You know, in nursing, every single leap forward in patient care, it all starts with a question. But how do we get from that moment of curiosity to actual rigorous science? Well, the answer is the hypothesis. It's the essential tool that takes a big, broad question and sharpens it into a prediction we can actually test. So let's break down how it all works.
So, here's our game plan. First, we're going to nail down what a hypothesis really is. Then, we're going to look at it through 4 different lenses: its scope, the kind of relationship it's talking about, the prediction it's making, and finally, how we set it up for testing. Then, we'll tie it all together and talk about why this is so critical for the care we provide every day.
Okay, so every great study kicks off with a question, right? But here's the thing. A question all by itself is just too broad to test. It doesn't have the focus we need to do real science. So we have to refine it. We have to sharpen it into something we can actually measure.
Take a question like this one. Does a new patient education program actually work? It's a great question, a really important one. But from a scientific standpoint, it's pretty vague. What does work even mean? Better compliance? Fewer readmissions? Higher patient satisfaction? See? If we can't define it, we can't measure it. And that is exactly where the hypothesis comes in to save the day.
A hypothesis is that formal statement. It's a super clear, precise prediction that takes that big general problem and makes it testable. It forces us to get specific about what we're looking for, who we're studying, and what we think is going to happen.
All right, let's look through our first lens. We're talking about scope. And really, the question here is simple. How many moving parts are we trying to juggle in our prediction? Is it simple, or is it a little more complex?
A simple hypothesis keeps things really focused. It's a one-to-one prediction, a straight line from A to B. A complex hypothesis, on the other hand, starts to paint a much bigger, more intricate picture. It looks at how a whole bunch of different factors might be interacting with each other.
Here we go, a perfect example of a simple hypothesis. We have one clear cause, our independent variable, aerobic exercise. And we have one clear effect, the dependent variable, blood pressure. It's clean, it's focused, and it's totally testable. Okay, now let's add a little spice. We've still got exercise affecting blood pressure, but notice we've brought in a third variable, age. Now we're not just saying exercise helps, we're predicting that this relationship actually changes depending on whether the patient is an adult or elderly. See? That's what makes it complex.
Next up, let's switch to our second lens relationship. This is a big one. This is all about defining the nature of the connection we're predicting. Are we just saying two things seem to be connected, or are we making a much stronger claim that one thing causes the other?
An associative hypothesis is all about correlation. It's like saying, hey, when A changes, B tends to change too. But a causal hypothesis, whoa, that's a much bolder claim. That says if I change A, it will make B change. And that distinction is absolutely fundamental to how a study gets designed.
This is a classic example of an associative hypothesis. We see a link, a connection between TV hours and BMI. But notice, it stops short of saying that watching more TV causes weight gain. I mean, there could be other factors, right? Like diet or activity levels. The variables just seem to move together.
Now compare that to this. This is a whole different ballgame. This is a causal hypothesis. It's predicting a direct cause and effect. It's saying the specific type of oral care, the intervention we control, is expected to directly cause a change in pneumonia rates. This is the language of an experiment.
All right, time for lens number 3, the prediction itself. This is all about how confident we are. Based on what we already know from past research, are we willing to place a bet on the specific direction of the outcome? Or are we just saying, hey, I think something's going on here, but we're not sure which way it'll go?
So a directional hypothesis makes a specific bet. It predicts scores will go up, or one group will do better, or something will be lower. A non-directional hypothesis is more open-ended. It's basically saying we're pretty sure there's a connection here, but it doesn't call the shot on exactly how it plays out.
In this directional example, the prediction is crystal clear. As knowledge goes up, attitude becomes more positive. We're not just saying they're related, we're specifying the positive direction of that relationship. We're calling our shot.
Now check out the non-directional version. We're still predicting a link between knowledge and attitude, but the outcome is left wide open. Maybe more knowledge makes you more positive, or maybe it makes you more critical and negative. This hypothesis just says, hey, there's a relationship, period. And that brings us to our fourth and final lens, which is honestly the most critical one for actually doing a study: testing.
To do any kind of statistical analysis, we have to set up two competing ideas. Think of it like a boxing match, where we see which idea the evidence actually supports.
So, in this corner, we've got the research hypothesis, also known as H1. This is our prediction, our challenger, the idea that there is an effect. And in the other corner, we have the reigning champ, the null hypothesis, or H0. This is the default position that there's no effect, no relationship, nothing to see here. Now here's where statistics is so brilliant. We never actually prove our research hypothesis is true. Instead, our entire goal is to gather so much compelling evidence that we can confidently reject the null hypothesis. We're trying to prove that the idea of nothing is happening is just not believable anymore.
So really, every statistical test you ever see is this fundamental showdown, the null hypothesis versus the research hypothesis. We collect all our data to see if we have enough evidence to land the knockout blow on the null, which in turn gives powerful support to our own prediction.
Okay, so why? Why do all these classifications and labels matter? Well, it's because a well-defined hypothesis is the bridge that takes us from a simple clinical question to a reliable, trustworthy answer. It's the blueprint we use to build the very foundation of evidence-based nursing.
I want you to think of these 4 lenses as your personal toolkit. Anytime you're designing a study or even just reading a research article, you can run through this checklist in your head. Is it simple or complex, associative or causal? It instantly clarifies the entire point of the study.
At the end of the day, a strong hypothesis gives our research direction, it gives it focus. It makes sure our work isn't built on just a hunch, but on a prediction that we can test, retest, and ultimately use to build knowledge and improve the way we care for our patients.
So I'm going to leave you with a little challenge. Think about your own work, your own clinical practice, and the questions you probably ask yourself every single day. With these tools in your pocket, how could you take one of those questions and turn it into a sharp, clear, testable hypothesis that could maybe lead to the next big breakthrough?